Okay, 6.1 slope fields. To start off with slope fields, we need to know how to solve differential equations. Differential equation is just an equation involving a derivative. And normally when we derive, we have this. I'm just making this up. But differential equations are sometimes written, I can't even speak, like this. So this is still a differential equation. Now these, you see how it's no longer dy over dx? Well, this is what is referred to as separating the variables. We want the y's on one side and the x's on the other. And on the AP exam, whenever you solve a differential equation, your first step needs to be separating the variables. Your answer could be totally correct, but if you never actually separate the variables, then you lose all the points, because usually the whole separating of the variables, they check that for the FRQs, because that's when they actually check you or check your work. It's no longer a multiple choice. Okay, so diffie-Qs, that's what we're working with today, and that's what they're called, diffie-Qs. Okay, example 1. Find all functions y that satisfy dy dx equals secant squared x minus 2x plus 5. Okay, so find all of the functions that would actually work with this derivative. So basically, I'm asking you to find a equation that I can derive and get this as my derivative. So remember when we did definite and indefinite integrals? An indefinite integral, I definitely don't know what the original equation is, right? So since I don't know what it is, we always add the plus c. And this is the constant of integration. So diffie-Qs kind of work with the constant of integration because I'm asking you to find any function that could work to be derived to get secant squared x minus 2x plus 5. So then that should tell you that your answer should have a c in it, should have plus c. In order to find the original equation, I'm just basically going to antiderive. And antideriving is just integrating. Okay, so step 1. Let me move this out of the way. You're going to take your function, dy dx equals secant squared x minus 2x plus 5. And you're going to separate the variables. So let me get rid of the dx. And the way to do that algebraically, right, is just multiply both sides by dx. So I get dy equals secant squared x minus 2x plus 5 dx. Okay, next step. I'm going to antiderive. So antideriving, or the antiderivative, it could be found by integrating. So I'm going to integrate both of the sides of this equation. So the derivative, or the antiderivative of dy, basically dy is us deriving y. So if we integrate the dy, we get y. Okay, because let me elaborate on this. The integral of dy, this is equal to me saying the integral of 1 dy. And if you integrate 1 with respect to y, because that's what it's telling me, I get y. Just like if you were to integrate 1 dx, if you integrate that, it's just x. Okay, so I'll let him explain that. So the integral of dy is just y. And then, let's see, what do I have to derive to get secant squared? Okay, so if you need to look at your blue sheet with all of your the formulas for the derivatives and the integrals, please do so, okay? But you derive tangent to get secant squared x. So if you antiderive secant squared x, the integral of that is tangent x. Minus 2x, so minus, and then 2x x becomes squared, but then I would divide that 2, so it cancels the 2 that was already there. And then plus 5, but 5 becomes 5x. And then because I'm not really sure if there was or wasn't a constant at the end, I'm going to write plus c. So this is my my antiderivative, my integral. I integrated. So find all functions y that satisfy dy dx. So because of the c, this can be all of the functions. This could be tangent x minus x squared plus 5x plus 1. This could be tangent x minus x squared plus 5x minus 9. Okay, these all are possible equations, possible functions of y, that when I derive them, I'll get secant squared x minus 2x plus 5. Okay, example 2, solving an initial value problem. We've done this already. We have solved problems with initial values. This is just now with diffie q's, so I want to make sure that we separate the variables and we integrate both sides. So find the particular solution to the equation dy dx equals e to the x minus 6x squared. So dy dx equals e to the x minus 6x squared. So this is the function I'm going to antiderive. And my initial conditions are this right here. The original function, when x is 1, y is 0. So first off, separate the variables. So dy equals e to the x minus 6x squared dx. And then integrate both sides. So I get y equals the integral of e to the x. Okay, if you remember, the derivative of e to the x is e to the x. So the integral of it is going to be e to the x. Minus 6x squared. So x is now going to be x cubed, but then I would divide by my new exponent. So that 6 is going to be 6 divided by 3. So that's 2. And then, of course, plus c. So there's my integral. Okay, now, if you remember, when you did initial conditions before, you used the initial conditions to figure out what c actually equaled. So you could actually find just one particular solution. In example 1, we found an equation that can be any equation as long as we change the c, right? It could be an infinite amount of equations. I'm just going to change the c. Here, I want to know what c equals, and I want one particular solution. I want one equation, not a whole bunch of them. Okay, so this is the original function. So now you are going to use your initial conditions. I want to use this. So x equals 1 and y equals 0. So you would plug that in. So y is 0 and x is 1. So e to the 1 minus 2 times 1 cubed plus c. And then you're going to solve this to figure out what c is. So 0 equals e to the 1 is just e minus 2 plus c. So subtract e, subtract 2. Subtract e, add 2, and that's what c equals. So add the 2, subtract the e, and c equals 2 minus e. So now that I know that c is all of this stuff, my equation over here, so y equals e to the x minus 2x cubed plus 2 minus e. And this is my equation. This is my particular solution. When it says the word particular, you should be like, okay, I'm only going to find one. And if you have initial conditions, that should be a key word for you to be like, okay, I'm looking for one equation because I'm going to find the value of c. Okay, find the particular solution to the equation. So same thing, whose graph passes through the point 0, 3. So here's my x and here's my y. I'm going to use them to find what c equals. And then I'm going to end up with one equation, my particular solution. Okay, so dy dx equals 2x minus secant squared x. Separate the variables. So dy equals 2x minus secant squared x dx. And then integrate. So on the left side I have y, and on the right side 2x becomes x squared divided by 2, so that 2 gets divided away, minus, again, secant squared x, that came from tangent, and then plus c. And then I'm going to use my initial conditions. My initial conditions were 0 and 3. So y is 3, x is 0. All right, unit circle. So here's 0. At 0, my coordinates are 1, 0. So this is the cosine and the sine. Okay, tangent of 0. That is sine divided by cosine, which is 0. So back over here, I have 3 equals 0 minus 0 plus c. So c is 3. So now that I know c is 3, I go back to the antiderivative, which is right here. And I'm going to be a little lazy, right? So plus c is now plus 3. Okay? All right. Example 4, graph the family of functions that solve the differential equations dy dx equals cosine x. Okay, so remember, this is the derivative right here. And, okay, what would I usually derive to get cosine? And hopefully you're thinking, oh, it's sine, right? And you would be correct. But see, what they want us to do is, they want us to graph the family. Okay, in a family, usually more than one person, more than one thing. So they want us to graph the family of functions that would actually work for this derivative. So that means plus c, and I'm going to show you how to do that on the calculator. Okay, so you're going to need a graphing calculator. Okay, so on the graphing calculator, this family of functions, I'm going to need different values of c. So what I want you to do is I want you to go to stat. There's a stat button. It's right here. And then you're going to go to edit on the top, right? So you see on the top, it's on edit, and then you're going to choose the first option, which is also edit. So you can hit 1 or hit enter because it's highlighted on the 1. And these, oh, let me slide this over. You can't really see it on the screen completely. Okay. Now these are lists, and we're going to fill in the first list. And I want to use -3, and then go down. Is that 33? Oy. Okay, so -3, go down. There we go. -2. Oh, this is getting really annoying. -2. Okay, I'm gonna fill it in. -3, -2, -1, 0, 1, 2, and 3. Okay, so I filled it in. -3, -2, -1, 0, 1, 2, 3. Okay, so then you're done. I'm gonna hit second quit. Okay, so well, see, I hit second quit. This computer online is really not working so well. Come on. Just clear out of there. Okay. And then after hitting stat edit and then turning in your list, you're going to go to y equals, because you're just going to graph this. So I want you to be able to see or be able to do it on the calculator and see stuff. Okay, so we're going to graph solutions to dy dx cosine x. And the solutions would be sine. So you're going to graph sine. So sine x, close the parentheses. Okay. Sine. I don't know what's wrong with this thing. X, close the parentheses, and then plus, and essentially where you're going to plus is the c. But since c can be so many different things, that's why we did our list. I just want to do from -3 to 3. So just those 7 values. Of course, it could be an infinite amount. And to enter the list, you're going to hit second, and then you're going to hit number 1. And as you can see above number 1, it has like a little L1. That's the list. And of course, it didn't work. Second, 1. Oh, okay. Something's wrong with this calculator. Hold on. Okay, so it says L1. So then you're just going to graph. And it's going to draw me a family of solutions for dy dx equals cosine x. And this family of solutions is just going to be a bunch of sine of x with a different c value. Now, again, I could have made it a whole bunch, but I only picked the 7 values. And so see, these are all sine. So let's see, we've got 4, 5. We've got 2 more to go. All right, so there are my 7. I could have done more, I could have done less. You could make the window a little smaller so it fills it up, but this is a family of the functions, a family of functions that will actually have the derivative of cosine x. Okay, here, determine which graph shows the solution of dy dx equals negative x with initial value y negative 1 equals 1. Notice if all three, the negative 1, 1 is highlighted. I'm looking for the original function that would work for this derivative. And the thing is, this kind of problem, I want to be able to do it without actually, like, okay, negative x, right? So if you antiderive or you integrate that, okay, so this already has a 1, so you would add 1, right? And then you would divide by that new number. So here's your original equation. So then you would be looking for that. And as easy as that is, I want you to understand that you can do this without having to integrate and just very quickly analyzing the function. Because in this class, you do need to know how to analyze a function to a certain extent. So the way I want you to look at this is this. dy dx equals negative x. These are slopes, right? These are all, any number I plug in there, what my result is going to be a slope. My result is going to be a slope. So if you think about this numerically, right? Whenever x, my x value, is negative, so when x is negative, and in this class we denote negativity by saying x is smaller than 0, then my slope is going to be positive, right? Because if I enter a negative number in here, a negative times a negative is going to be positive. So dy dx is going to be bigger than 0. Whenever my x is actually a positive number, bigger than 0, right? When I plug it in there, that negative in the front is going to make my slope negative. So very quickly, analyzing these graphs, which one of these is going to have negative slopes whenever x is bigger than 0 and positive slopes whenever x is smaller than 0? So A, the slope is all negative. Okay, so that's not going to work. I'm going to jump to C, because obviously, hopefully, you know what this looks like, and you know that the answer is B. But C, here's 0, right, for x. On the left side, which means x is smaller than 0, right, which would be this right here that I'm talking about, x smaller than 0, I need my slope to be bigger than 0. I need my slope to be positive. Well, if you look, these slopes are negative. And for the next one, when x is bigger than 0, so on the right, according to this, I need dy dx to be less than 0, so I need my slopes to be negative. They're actually positive. So that makes C not my answer. And then B. Here's 0. For the left side, for when x was smaller than 0, I needed my slopes to be positive, and they sure are. And when x was bigger than 0, I needed my slopes to be negative, which they sure are. I mean, of course, this works, right? But if you're ever asked to analyze something like this, then you can say, okay, you know, how can I determine analytically, how can I analyze this and determine, okay, this is my solution because, not because I integrated, but because of the slopes. And all the stuff I wrote in blue, that is why. Okay. Explain why y equals x squared could not be a solution to the differential equations with slope fields shown below. Okay, so kind of similar to before, but now I want to recall, what does this look like? So y equals x squared is basically something like this, right? My drawing's not perfect. Looking at this slope field, if I were to follow this slope field, it kind of looks like I have something like this, right? I mean, just about anywhere I draw, it looks like I have something like that. So maybe it goes like this, right? So it doesn't even look like x squared. But putting that aside, let's look at the slopes again. For x squared, my slopes on the left are negative, and on the right, they're positive. So on the first quadrant, my slopes are positive. In the second quadrant, my slopes are negative. So if I look over here, in the first quadrant, my slopes are positive. So that checks out, right? Checky, checky. But in the second quadrant, my slopes, oh, they're positive. I needed them to be negative, right? So that right there alone is a good reason why. Y equals x squared couldn't be a solution to the differential equation with this slope field because in the second quadrant, y equals x squared has negative slope. But in this slope field, in the second quadrant, all of the slopes are positive. Okay, next. This is 2/3 of an AP Calc FRQ question from 2004. It says consider the differential equation dy dx equals x squared times the quantity y minus 1. Okay, on the axes provided, sketch a slope field for the given differential equation at the 12 points indicated. Okay, so this is basically the normal size of a slope field that they'd ask you to draw. It's not a lot of points. So real quick, a table. Make a table. Okay, so here's my table, and I only made so many boxes. There's 12 points. I only have 7 boxes. You can make more boxes if you like. But I'm looking at the equation, dy dx equals x squared times y minus 1. The easiest ones to do first are whatever values I can plug in, that will automatically give me 0, no matter what. For example, if I plug in x equals 0, it doesn't matter what y is. It's always, the equation is going to equal 0. So that's what I'm going to do. So for x is 0, any y value, does not matter. My slope is going to be 0. So let's go over here. So if x is 0 and let's say y is 0, my slope is going to be 0. So right here. Okay, x is 0 and y is 1. So my slope is still going to be 0. X is 0 and y is 2. My slope is still going to be 0. X is 0 and y is 3. Slope is still going to be 0. Hopefully you're getting my drift here. So that takes care of those 4 out of 12 points. Now, if I look at the equation, what other number could I plug in that will get me 0? So y minus 1. Well, let's see. If y was 1, that would be 1 minus 1, so that's 0. So whenever y is 1, it does not matter what x is. My slope is going to be 0. So at y equals 1, let's do x is 1 and y is 1. My slope is going to be 0. And let's do x is negative 1 and y is 1. My slope is going to be 0. So that right there is 4, 5, 6. So that leaves me with 6 left. And I only have 5 boxes. All right, so I'm just down 1. No big deal. Like I said, if you need more, you just make them. There you go. Okay, so we did x is 0, and we've done all possible y's are 1. So let's do x is negative 1. And so if x is negative 1, let's go ahead and do the only 2 that are left. Or sorry, the only 3 that are left. Y being 0, y being 2, and y being 3. So we're going to do those. So for x is positive 1, we still need to do y is 0, and y is 2, and y is 3. And that should take care of the last 6 points. Okay, so x is negative 1, so I plug that in, I get 1. I plug in 0 for y, and I get negative 1. So 1 times negative 1, that's negative 1. And then you're just going to plug all of these in, okay? I'm going to go ahead and pause this, and I'm going to fill out the rest. I'm confident that you can determine your number. It's just arithmetic, algebra, plugging in, and getting a value. Okay. Okay, those are the values I got. So now I'm going to actually do the slope. All right, now remember, real quickly, this is 0. 1 is basically like this. This is 1, right? And then 2 would have to be steeper, right? Oh, hold on. Got ahead of myself. So 2 would have to be steeper. So it would be like this. So this is 2. Okay? So this is 2. This is 1. See how the 2 is a little steeper? And then this is 0. Okay. Oh, and then negative is just reversed, facing the other direction. Okay, so for negative 1, 2. So right here, negative 1, 2, my slope is 1. So if I had to take a really good guess at what slope of 1 is, that would look like it. Okay, now negative 1, 3, my slope is 2. Okay, so then I need to make this steeper than the one from before. It doesn't have to be perfect. They actually want to see that it's steeper. They're not going to bust out a ruler and be like, nope, this is not 2 over 1. They want it to look steeper than the 1. Okay, 1, 0. So 1, 0. Oh, I just realized I skipped. Sorry. Negative 1, 0. So negative 1, 0, my slope is negative 1. So this is going to look like negative 1 to me. Okay. Okay, so where was I? 1, 0. So 1, 0 is also negative 1. So, and then 1, 2 is positive 2. Wait, did I say that right? Or sorry, it's positive 1. There we go. And then 1, 3 is positive 2. So, okay. And there you go. That's part A. This right here, I think, would get you a point. I know it's not a lot. If it's not 1 point, it gets you 2 points. FRQs are worth 9 points. This is part A, and I think this part A was 1 point or 2 points. And then part B was either 1 point or 2 points. The thing is, these two, part A and part B, got you 3 points. And 3 points out of 9 is not that bad, because this is the easier stuff. I left C out because I have to teach you something before we could do C, but we will do C. Okay, not today. B, while the slope field in part A is drawn at only 12 points, it is defined at every point in the xy plane. Describe all points in the xy plane for which the slopes are positive. Okay, so my slopes are going to be positive whenever x is not 0, right? Because we just learned that. And whenever x, or y, sorry, is not 1, right? Okay, so like look at this. Now, doing this top part here, we discovered that whenever x was 0, our slope was 0, right? Whenever y was 1, our slope was 0. So the x value does not matter. If you look at the equation, I could plug in anything in here, and it's always going to be positive, except for 0. Right? I can plug in negative 1. I can plug in negative 5, negative 20. It's going to be positive. So on the x front, in order to make my slopes all positive, x doesn't really matter. X can be anything except for 0. So I want to know, they want us to describe all the points where the slopes are going to be positive. Well, so for right now, I'm just going to be like, okay, x cannot be 0. but it can be anything else. All right, so now y's. So looking up here, if you remember, like I said, when y was 1, our slope was 0. Now looking at the equation, okay, so what numbers can I not put in here in order to make sure my result is positive? So if y is 1, we get 0, so we can't put 1 in. If y is 2, we get a big number. 2 minus 1, or not a big number, sorry, a positive number. So 2 minus 1, that's 1. So 2 is okay. 3, 4, 5, 6, the bigger the number, the bigger the y, we're okay, the number is positive. But the smaller the y, that's when it starts getting fishy. So if I plug in 1, 1 minus 1, that's 0. So right there, starting at 1, if I plug in 0, let's see, 0 minus 1 is negative 1. So that has the potential of making this slope negative, right? Because if my x squared is positive, a negative times a positive is negative. So if I plug in negative 1, now I have negative 2. So basically, if I keep going, the smaller the number, then my slope could be negative. So we go back over here. X can't be 0, but we just discovered that y can't be 1. It can't be 0. It can't be negative 1. It can't be negative 2. It can't be any negative number. So y has to be positive, right? But not only does it have to be positive, it can't be 1. So y has to be bigger than 1. Okay? It could be 1.5. It could be 1.1. It could be 1.001. But it cannot be 1. So now let's write this in a sentence properly. So slopes will be positive, right? That's what we're trying to make sure. For any x, it could be any x, but not 0, right? But for any x, but x equals 0. And any y greater than 1. And there you go. And right here, folks, 3 points on the FRQs. The last part is the part with 6 points, but it's just diffie-q. It's a diffie-q. They want you to solve the diffie-q. The only reason I haven't done it is because it involves E, and I haven't shown you how to do that yet. Okay, so homework. 4 problems. It would be awesome if you tried to do them before coming to class. Next class, you can make up the quiz if you want. And I guess we'll be doing some more questions, some slope-related questions.